Good afternoon, everyone. This is Tong from Michigan State University. The topic today is weighting in multi-level models. So it will cover the following sections: background, literature review, simulation design, simulation results, summary, discussion, and limitations. So as we know, more and more researchers use survey to connect the data. Most survey programs use complex sampling designs such as unequal probability of selection, stratification, clustering to save time and money. So thus it is necessary to incorporate ways to get accurate parameter estimates and valid inferences. However, weighted multi-level estimates have been lately developed and minimum guidance has been left. So in order to cover the gaps of a current body of literature, to develop the methods on hierarchical linear model is very necessary. So two research questions were addressed in the present study. The first one is, how does MPML, I will explain MPML later in the literature. So MPML stands for multi-level pseudo maximum likelihood estimation method. So how do MPML estimators differ from unweighted estimator in multi-level models in the informative and non-informative sample design in terms of relative bias, root mean square error, and 95% confidence interval coverage rate? And second, how does intra-class correlation influences the performance of estimators under the informative and non-informative condition in terms of relative bias, root mean square error, and 95% confidence interval coverage rate? According to Lair and Ware, two-level linear mixed effect model can be expressed using these mathematical forms. So either full maximum likelihood or the restricted maximum likelihood estimation method is often used to estimate the unknown model parameter in a general linear mixed model. So Sears, Cassina, and McCullen define the likelihood function for a linear mixed model as follows. For computational convenience, the log likelihood function is more often used instead of this likelihood function. So in order to achieve valid inferences for the population, sampling weights must be used at all levels of the data. So far, many researchers have explored different estimation methods incorporating sampling weights for complex survey. This multi-level pseudo maximum likelihood estimation is the most widely used and flexible estimation method in multi-level models incorporating weights, which was first explored by these two guys, so Hasker, Scrondel, and Esperhoff. So actually, by Esperhoff, he started study this MPML actually in 24, and also he published another paper in 2026. So if weighting is incorporated into the analysis and the scaling procedures are also applied, the population function is directly estimated by weighting the sampling likelihood function, which is expressed as follows, as this function. So, and the sandwich variance estimator is employed to obtain standard errors. M+ implements this method using the robust variance estimator having the following information. Scaling actually is a primary tool for us to reduce bias, and two scaling techniques for multiple level models were introduced in the present study. Pufferman actually et al. Specified these two methods in 1998 using these two mathematical forms. And one is called cluster scaling method. The other is called effective cluster scaling method. Actually, E-cluster or cluster were especially used in M+. Monte Carlo correlation simulations were conducted. Here is a simulation design. So you can see there are three factors were manipulated One is the informativeness of selection. One is ICC. The other is estimation method. So informativeness has two levels, informativeness and non-informativeness. ICC has 5 levels, different levels from 0.5 to 0.01 and to 0.005. In educational setting, 0.1, 0.2, 0.3 are most common values of ICC in education setting. So 0.1 and 0.5 are extreme values. So that's are the two values I picked for extreme settings. And the other factor is the estimation method. I used 4. And so these 3 factors are fully crossed, which result in 2 by 5 by 4 equals 40. So there are 40 simulation settings in total. So the data simulation design mimics the empirical data design, ECHO-K, early childhood longitudinal studies of kindergarten 2011. So the true values of the parameters used in the simulation are obtained from this empirical data set using maximum likelihood estimation method. So I use the values here for reading in the simulation design. The data are generated using this equation. The 3 student level predictors are somewhat correlated, female SES. Pretest rural. So rural is a school level, and then female SES pretest. This is a student level. These 3 student level predictors are somewhat correlated, and correlation matrix is as follows. So in the informative condition, Poisson sampling is used, and schools are sampled with this probability formula. And students given selected school is sampled with this probability formula. In the non-informative condition, Poisson sampling is also employed, and schools are sampled with this probability formula, and students given selected school is sampled with this different probability formula. The 2 error terms are not part of the model. Although the schools and the students are sampled with unequal probability here, the inclusion probabilities are not related to the response variable here. So therefore, the sampling design here is non-informative. So 3 criteria were used to evaluate the quality of the estimator. Empirical relative bias, root mean square error, and a 95% confidence interval coverage rate. The relative bias is calculated using this formula. So in terms of Moutin 2002, if the absolute value of the relative bias is less than 10% of the true value, the estimator can consider it unbiased. So the root mean square error is defined as this. The root mean square error tells us how far the approximation will be from the true value on average. The smaller the better. The smaller the root mean square error is, the better the estimation is. The quality is higher. Coverage rate is set at 95%. It is recommended that coverage rate should be at least 0.91 by Moutin and Moutin 2002. That is at least 91% of the replications having true parameter values within the 95% confidence interval. The simulation results show that all the fixed effects are estimated without much bias and can be considered unbiased in both informative and non-informative condition in terms of Moutin 2002. So I just report the results for intercept and various components due to the time limit. The results are presented in terms of relative bias, root mean square error and coverage rate in the informative and non-informative condition. Each plot addresses two issues. One is comparisons of estimators. The other is effect of ICC. On average, the relative bias in the informative condition is comparatively larger than that in the non-informative condition. The most variability occurs for level 2 variance estimators in both conditions. This is you will realize that later after I introduced all the slides. But so this sentence I just mentioned actually is kind of a summary before I start to introduce each plot specifically. Now, specifically, in the informative condition, the intercept and the level 1 variance are estimated unbiasedly, except for the intercept estimate with unweighted estimator. The three weighted estimator performs quite similarly, you can see that, and much better than the unweighted, this black bar, than the unweighted estimator across all the levels of ICC for the intercept. For level 1 variance, all the estimators work quite well because they have the relative bias less than 10% in terms of mutant and mutant. So I use this criteria to evaluate the performance of relative bias. Among them, cluster skinning estimator outperforms the others. And the unweighted, this black bar, unweighted performs the worst. For level 2 variance, all the estimators do not work well when the ICC is extremely small. Even the best estimator here has the relative bias of over 80. So in general, the unweighted estimator works the best, and the raw weighted estimator is the worst. Now, as for the effect of ICC, as ICC increases, relative bias for the intercept with unweighted estimator increases as well, but no monotonic pattern can be found with 3 weighted estimators. So relative bias for level 1 variance increases as ICC increases with all the estimators, but the increase rate is so tiny that the pattern remains almost the same with all the estimators. So, however, for level 2 variance, there is a clear pattern for the relative bias. As ICC increases, the relative bias for level 2 variance decreases. In terms of root mean square error, on average, the root mean square error in the informative condition is larger than that in the non-informative condition. Specifically, in the informative condition, including sampling weights, decrease the root mean square error for the intercept and the level 1 variance, but increase the RMSE, the mean root mean square error for level 2 variance. So the 3 weighted estimators performs more efficiently than the unweighted method for intercept and the level 1 variance. The 3 weighted estimators perform quite similarly for the intercept, but for level 1 variance, the cluster scaling method, the red bar, works the most efficiently. For level 2 variance, the unweighted, the black bar, the unweighted method works most efficiently. The raw weighted the least. So as for the ICC, the effect of ICC, as ICC increases, the RMSE for intercept with unweighted method increases as well. But the RMSE with the 3 weighted estimators remains almost the same. You can see that. as ICC increases. For various components for this too, as ICC increases, the RMSE for level 1 variance decreases, and for level 2 variance increases, except for raw weighted estimator. So you can see, probably you can see that there is no clear pattern for this rule, but it's kind of, there is not much differences for the first 4, but it's increased for this method when the ICC is extremely large. But anyway, we cannot find any pattern for this. So in terms of a coverage rate, on average, the coverage rate in the informative condition is lower than that in the non-informative condition. The most variability occurs for the intercept in the informative condition, but level 2 varies in the non-informative condition. So because the unweighted estimator has a substantial higher relative bias for the intercept and the level 1 variance, we can see that, right? So the unweighted, this black bar, has substantially higher relative bias for the intercept and for level 1 variance, which needs to pool coverage, which needs to pool coverage rates for both of them. So the unweighted estimator has as low as 0 of coverage rate for the intercept and has 0.02 coverage rate for level 1 variance, this one. The 3 weighted estimators, although they do not have a coverage rate of 0.95 for the intercept, but they have the coverage rate around or over 0.91. So, and they have almost the same pattern of coverage rate for the intercept. For level 1 variance, the cluster scaling, the red bar, the cluster scaling estimator has the highest coverage rate among the 4 estimators. For level 2 variances, the raw weighted, okay, the green, the raw weighted estimator has as low as 0 of coverage rate, and it performs the worst among the 4. The unweighted estimator, the black bar, has the highest coverage rate. As for the ICC effect, the coverage rate for the intercept and the level 1 variance do not show monotonic decreasing or increasing pattern as the increase of ICC. Although there are some variations for the coverage rate for level 2 variance, no monotonic pattern can be found. So no ICC effect is found for coverage rate. Okay, let's introduce the results in non-informative condition. In the non-informative condition, in terms of relative bias, the intercept and the level 1 variance are estimated unbiasedly. The level 2 variance is estimated unbiasedly when ICC is extremely large. For the intercept, the unweighted estimator works the best in most cases. So for level 1 variance, the effective scaling estimator and unweighted estimator works better than the other 2. So for level 2 variance, no estimator works well when ICC is extremely small. That is when ICC is 0.01. The effective scaling estimator and the unweighted, this one and this one, unweighted estimator works better than the other 2. So raw weighted, the green one, the raw weighted estimator needs to be used with caution for various components. So, sorry, I forgot the ICC. As for the effect of ICC, as ICC increases, the relative bias for the intercept with 3 weighted estimators decreases. while the relative bias increases with unweighted, the black bar, with the unweighted estimator. As for level 1 variance, the pattern remains almost the same. You can see that. As the ICC increases. For level 2 variance, as the ICC increases, the relative bias decreases. So in terms of root mean square error, and in the non-informative condition, including sampling weights increases the root mean square error for all the 3 parameters, for all these 3 parameters. So unweighted method works most efficiently across all the conditions. As for the effect of ICC, RMSE remains almost the same as the increase of ICC for the intercept. The RMSE decreases for the level 1 variance and increases for the level 2 variance as the ICC increases. Now, coverage rate in the non-informative condition. We can see that the coverage rate for the intercept are almost the same across all the estimators. The unweighted, for the various components, the unweighted, so black bar, the unweighted and effective estimators, so blue. So the unweighted and the effective estimators have higher coverage than that for the other 2 estimators for the variance components, for level 1 and the level 2 variance. So raw weighted estimators, the green, has the least coverage rate for level 1 variance and level 2 variances. As for the effect of ICC, as ICC increases, the coverage rate for the intercept and the level 1 variance show not much changes across all the estimators. Although there are some variations for the coverage rate of level 2 variance, it is hard to find a unified pattern across all the estimators here. Here's the result. So on average, relative bias and root mean square error in the informative condition are larger than those in the non-informative condition. However, the coverage rate in the informative condition is lower than that in the non-informative condition. And second, in the informative condition, the weighted estimators outperform the unweighted for the intercept and level 1 variance in terms of relative bias. However, the unweighted estimators performs the best for level 2 variance. In the non-informative condition, the unweighted estimators performs the best or the second best for the intercept and the variance components in terms of bias. When the ICC is extremely small, none of the estimators work well in both conditions. Number 3, in the informative condition, including sampling weights decreases root mean square error for the intercept and level 1 variance, but increases it for level 2 variances. 3 weighted estimators perform equally well for the intercept, but cluster scanning estimators perform most efficiently for level 1 variance. The unweighted estimators performs the least. For level 2 variance, the unweighted estimators performs the most efficiently. The raw weighted estimator performs the least efficient. So, however, in the non-informative condition, including sampling weights increases root mean square error for all the parameters. So the unweighted estimators perform the most efficiently for all the parameters. Number 4, in the informative condition, the weighted estimators give better coverage rate for the intercept and level 1 variance, but the unweighted estimators have a higher coverage rate for level 2 variance. In the non-informative condition, the unweighted estimators has the highest or the second highest coverage rate for all the parameters. The effect of ICC actually is related to relative bias and root mean square error, but not sensitive to coverage rate. the effect of ICC is more obvious for level 2 variance estimators. As the ICC increases, the bias decreases for level 2 variance in both conditions. However, the increasing rate is so small that we cannot see an increasing pattern of the bias for level 1 variance as ICC increases. The unweighted estimator has an increasing bias for the intercept as the increase of ICC in both conditions. Discussions. So in one sentence, we might say some of the conclusions in the current study, no, I should say the prior conclusions in the prior studies have been confirmed. Some of the conclusions in the prior studies have been confirmed in the current study, but some are not. So, so here there are some discussions here. The first one is Chai and Pufferman et al. Found that the unweighted method produced bias estimates for intercept and level 2 variance in the informative condition. This is partially confirmed in this study. Unweighted estimator produce biased estimates for the intercept, but it only does not work well when ICC is 0.01 in the informative condition. And second, and Chai also point out that including the sampling weights substantially increase the mean square error. This is only confirmed in the non-informative condition. In the informative condition in the current study, it is true for level 2 variance. Number 3, Asperhoff and Mutan reported that this multi-level pseudo maximum likelihood estimation method outperforms substantially the other estimators. In the current study, the unweighted estimator outperforms the others for level 2 variance in the informative condition. Number 4, Asperhoff and Mutan, I don't know how to pronounce this, and Rai found that the bias increases for all the parameters as the ICC decreases. It is proved by level 2 variance in the present study. However, bias remains almost the same for level 1 variance. For the intercept, the bias with unweighted estimator increases as the ICC increases. So when I read the prior papers, actually, after I've done this paper, I can still say that there is no consistent conclusion about which method performs best in all the conditions. So because Asperhoff and Chai also point that out, so I still get the same conclusion as the prior authors or researchers. So of course, there are many limitations in this study. The first one is I only random intercept is used in this study. Probably it is more real to treat slope as random. And second, the scaling weights is the primary tool to reduce the bias in the present study. There is another way, probably trimming weights, which is not considered in the current study. It might be alternative for scaling weights. Number 3, more levels of informativeness to be studied or necessary, because I just have 2 levels of informativeness of selection. If we have more levels of informativeness to be studied, it might tell us under which condition the parameter might be estimated unbiasedly. Number 4, multi-stage sampling in simulation is simplified in the present study, so it does not reflect reality well. So in the future, we might increase the model complexity. Increasing the model complexity and examining different models might explain why ICC does not change in certain conditions in the current study. And second, probably we may more studies are needed, especially in unideal conditions. So the current study used large number of clusters. So here in simulation, I use 150 schools. As Verhoef and Moutin and the other two papers point out that the performance of estimators might suffer from small number of clusters. So more studies needed to work on ideal conditions. And I think this might be more real. So, and number 3 is it is necessary to enhance multi-level models since no unified conclusions can be drawn. As Verhoef and Moutin in 2010 stated that Bayesian estimation method might be alternative to maximum likelihood estimation when the sample size is small, if we have informative priors. But so far, few comparisons were made between them. So we might try, we can also compare other two. For example, pseudo maximum likelihood estimation with Bayesian estimation likelihood. And also there is another one, iterative generalized least square estimation method. These 3 methods can be compared using different conditions. Because here I just use 3 factors. I just manipulated the 3 factors in current study. So probably we may control or manipulate cluster size in the future and using the other 2 or other multi-level estimation method to compare them. So that's all. Thank you.
Thank you for the presentation, Tong. Does anybody have any questions they'd like to enter into the chat? Not seeing any. Thank you everybody for attending and thank you for the presentation.
Thank you.